Hello everyone, welcome back. In this video, we're going to discuss the memory of the RFID card. Of course, the RFID card has a memory where it has to store data we write on it, adding details it holds like UID, like keys, authentication keys, and access bits. This is a tabular representation of the memory map. Memory map is divided into sectors, 16 sectors, counted from 0 to 15, and each sector has 4 blocks. And a block is made up of 16 bytes of capacity. The first block of the memory holds UID, unique identification of the card. And for that reason, it's called the header. And there is also trailers. Trailers are the last blocks of every sector. So since we have 16 sectors, we have 16 trailers. Keep in mind that we have one header. So in the memory, we have 16 sectors, whereby each sector is made up of 4 blocks. And the first block, that's the first block in the first sector, is a header block, whereby the UID is stored, and every fourth block in each sector is a trailer that holds a key. There are 6 bytes for key A. There are also 6 bytes for key B and 4 bytes for access bit. Access bits are here to govern how the sector is accessed. And this is the trailer, and this is the permission. This shows how the operation on the trailer are performed. 001 means data on this trailer can be written, can be read using either key A or key B, and to write, this is what this one means. To write, you need necessarily key B as a layer of security. You can read, that's okay to read, using either key A or key B, but to write, because this trailer block holds information so important that anyone shouldn't modify as they want, it has this layer of security whereby key A and key B can be used to read, but for writing, for making any modification, you need necessarily key B. And as you can see, for other blocks, including the header, you have a 000. It means you can perform the operations using either key B or key A, either reading and writing. Maybe you say you are kidding, because how come the header can be modified such easily? Of course, you can't modify the header. 000 at the header block means it aligns with the conditions of other blocks as opposed to the trailer block. But this has been locked using hardware impost lock. So yeah, this is it. Okay. Now that you understand the tabular representation of the memory map, you have to know that there is another representation, a 3D representation. Maybe that adds some more clarification. So from bottom to the top, these are sectors. This is a sector. It's made up of 4 blocks. The first sector is made up of this header block, the red one, and 2 ordinary blocks or data blocks, and then the trailer. We have trailers from as the last block from bottom to the top, and then we have normal blocks. This is a sector, an ordinary sector. From 1 to 15, these are ordinary sectors. We will have 3 blocks and a trailer block. And this is a special sector, sector 0, special because it has a header and of course a trailer. Now that you understand the structure of the memory, we can calculate the actual writable memory. This is the memory we are allowed to write data on and of course read. The write memory is the total memory excluding the trailers and the header. This is how we can calculate it. We have 16 sectors. Each sector is made up of 4 blocks, and each block has 16 bytes. So by making a multiplication, we get 24 bytes as total memory, and this is 1 kilobyte. But this is the total, just the total. So when we calculate the reserved memory, we consider the header and the trailers. So we have a trailer block at each sector, and we have a header block with 16 bytes, adding the bytes reserved to trailers and the bytes reserved to the header, we get 272 bytes. So we can take the total memory and subtract the reserved memory, getting 752 bytes as writable memory. And for verification, we can calculate writable memory considering that we have 2 blocks on sector 0, which equals to 32 bytes, and we have other 15 sectors whereby we have 3 writable blocks, and that goes up to 720 bytes that are writable. And making summation, we get the total writable memory 32 plus 720, and that equals 752 bytes. Yeah, verified. Okay, so this is it. We have 732 bytes where we can write anything and read anything. Okay, now let's look at the code that will enable us to read the memory map. We have the code here. Don't worry, the code is uploaded to GitHub or in this repository, RFID Technology Made Easy. You can get the code we are using here. We are using the code memory map PICC and memory map PICC. It's the codes here. Okay, here is the code. So you don't need to worry. You have the same code. So I have connected my Arduino Uno. Yeah. This is the Arduino Uno, and this is the RFID card reader. The code is using the SPI library because the RFID reader is using SPI, and this library from MIFARE, the manufacturer, because we need this library in order to be able to use this. And the reset pin is connected to pin 9, while a slave selector pin is connected to pin number 10. This is the object creation or instantiation that accepts two parameters, the slave selector and reset pin. And this is to start the serial monitor. This is to wait for the serial monitor to open, and then we initialize the SPI communication protocol. And this is to set the sensitivity to the highest value in order to be able to detect the card when it's a little bit far. And this is to initialize the card, the PCD standing for proximity coupling device. This device is the PCD, while this is the PICC. PICC standing for proximity integrated circuit card. And this is to dump the version of the firmware used to this card. It has a firmware. This card has firmware, and it will be printed even before bringing the card closer. And then it will display the information it's going to print. Yeah, when you bring the card to the proximity. So in the loop, when the card is not detected, the code will exit, the function will exit, and when the card detected cannot be read, also the code will exit. And in the case when the card is detected and it can be read, then the card will dump the information on it to the serial monitor with the microcontroller. So let's upload the code. Codes uploaded, and let's open the serial monitor. This is the firmware. It's in hexadecimal B2, and then when we bring the card to the proximity, the card is brought to the proximity and read information. And this is the same or the similar information we've been analyzing here, here. Okay, if you were wondering how we got this data, now you understand. Okay, this is the UID, this is the SAK. SAK means select acknowledge. This is the number given to a device to be able to identify the manufacturer and to know the international ISO protocol used. And this is for us to know it's manufactured by MIFARE and it's 1 kilobyte. And this is the memory structure as discussed. Thank you everyone for your attention. I hope you understand now better the memory of the RFID card, and you know the amount of memory you can use to write and read your data. Let's see each other in the next video. Bye.